Hello and welcome back. In this video, we will look at LeNet. So, LeNet 5 as it was called, dubbed, was first published, reported back in 1998. It was one of the earliest instances of convolutional neural networks used for image recognition. Its specific application was for digit recognition and apparently had commercial application where it was used to read millions of checks in banks. So, this network serves as a kind of template for most of the modern networks that we see today. So, we will just briefly look at it and see some of the salient features of this network. So, this network took as input about 32 cross 32 images. This network was trained with images from the MNIST database. So, the images were around the size 28 by 28 and then these images were then further modified to in fact kind of like a data augmentation where several distortions were introduced and used for training this network. So, it took as input images of size 32 by 32. So, basically images of digits, handwritten digits which has been discretized, scanned and discretized. So, the typical architecture is basically input followed by a convolution followed by a pooling layer, and this was repeated leading to finally to a couple of fully connected layers and an output, which is basically 1 of 10 classification. You have to classify digits 0 to 9. Network had about 60,000 parameters. Okay, it has several interesting concepts here. For instance, the first layer had 5 by 5 convolution, no zero padding, which gives rise to a 28 cross 28 output, followed by a 2 by 2 pooling. This is an average pooling operation. So, basically 2 by 2 average pooling with a stride of 2. So, the average pooling basically the output is basically the average of the 4 elements in that 2 by 2 area of the filter, then followed by a 5 by 5 cross 5 convolution, again no padding, which gives rise to a 10 by 10 output. Then subsequently another 5 by 5 convolution gives, and then a max pooling which gives rise to a 16 cross 5 cross 5 maps. Now, when we do a 5 cross 5 convolution on top of these maps, it is basically the same as doing a fully connected layer, but then the paper actually also calls this a convolution layer. This is also a convolution layer. So, we start with the 32 by 32 input here, perform 5 cross 5 convolutions followed by max pooling, and then one more 5 cross 5 convolution followed by a max pooling, okay, which gives rise to 5 cross 5 feature maps, 16 of them, and we do again 5 cross 5 convolutions on that, giving rise to 121 cross 1 outputs. That is the interesting part. The author also mentioned, Lakun is the first author of this paper. He mentions that this is what right now we call this as fully convolutional layers, right. So, if we have an input which is bigger than 32 cross 32, then the number of feature maps in this, the size of the feature maps in this layer would be higher than 1 cross 1. In fact, if you think about, let us say, a 64 cross 64 input, one way of looking at it is that we can slide the entire network across the 64 cross 64 with a stride of 32, and we can actually get a 2 cross 2 output here. So, if you can think about it that way, and then finally a fully connected layer, and then to a decision layer or the output layer. You can use softmax here if you want. Okay. So, this has several things which are repeated even now in current networks. One is that as you go deeper into the network, starting from the input, the size of the feature maps typically shrink because of the convolutions, also by the pooling operation, which is actually a subsampling operation. And not only that, as the size of the feature maps decrease, the number of feature maps increases. So, in the end we have 121 cross 1 feature maps, and on the first layer we have about 6 feature maps of size 28 by 28. So, this general principle is, you will see, is reflected in the current architectures also. So, this network achieved state of the art results in 1998 for digit recognition based on the MNIST digit database. In this video we will look at AlexNet, which was this work was done in 2012. So, AlexNet was the entry to the ImageNet large scale image recognition challenge, and this was one of the first CNNs to be entered into the challenge, and it actually beat all its nearest competitor by more than 10 percentage points. Okay. So, this was a deep neural network with about 7 layers, okay, and 60 million parameters. Okay. So, this was the structure of this network is the architecture of the network is very similar in terms of very similar to LeNet 5 in terms of the convolution and max pooling operations, but then it had various other innovations in it, as we will see in this video. So, just to give a brief overview of this network. So, the ImageNet challenge, the input, these are RGB images. So, the input layer at size 224 cross 24 cross 3. Some sources have pointed out that it should be actually 227 cross 227 in order for the output in the second layer to be consistent. Okay. So, the first layer, first convolution layer had a 11 cross 11 filter, 11 cross 11 filter with a stride of 4, giving rise to 96 feature maps of size 55 by 55, and then we have a max pooling operation here, max pooling operation using a 3 cross 3 kernel and a stride of 2, so which leads to effectively halving the size of your feature maps, again followed by 5 cross 5 convolutions. So, this is the typical structure. So, we have all max pooling operations are 3 cross 3 with a stride of 2, and all the convolution operations are again 5 cross 5 with a stride of 1. Okay. So, the layers you see here, the intermediate convolution layers you see here without any max pooling, they had convolution with padding 1 to preserve the size of the network, and in this case, so I earlier mentioned that 5 cross 5 for almost all of the convolution operations, but in these intermediate layers the filter kernel size was 3 cross 3 for all these 3. Okay. And they had a padding 1. So, in these boxes the intermediate convolution layers that I shown here has where convolution filter kernels of size 3 cross 3 with a pad of 1 to preserve the size of the feature maps, followed by a max pooling and then a fully connected layers, 2 fully connected layers and an output which is 1 of 1000. So, the ImageNet classification challenge provides you 1000 image categories and you have to classify them as 1 of 1000. So, a pretty deep network at about 7 layers. So, if you count it is about 1, 2, about 5 convolution layers, about 3 max pooling. Okay. Typically about 7 layers which included convolution as well as the densely connected layers. So, if you just count the convolution plus the fully connected layers, you will have about 7 of them. This network also had a normalization layer normalization, where it is called local contrast normalization. This was done by, if you look at a particular pixel or an activation in a feature map, you normalize its value by looking at the adjacent feature maps at the corresponding feature location. So, this was, but of course, this is no longer done. This was the one off thing that was done for this particular realization of the network. So, another thing that this network again had, if you look at this network, a lot of the computations happen in the earlier layers, because you have 11 cross 11 convolutions, 5 cross 5 and 3 cross 3 convolutions. Okay. But if you look at the fully connected layers in the end, lots of parameters here. Most of the parameters come from here, because you see if you look at these 2 fully connected layers, this is like 4096 times 4096 weights. Okay. And if you look at the max pooling following this is for 256 cross 13 cross 13 as input to the max pooling layer with a stride of 2. So, you will have about 256 cross in this case, if you have pooling 3 by 3, you have 2 cross 5 cross 5, I think, and you unroll this and follow up with a fully connected layer to a 4096 activations. Okay. So, a lot of the parameters occur towards the end, and a lot of the computations are at the input side of the layer of the network, because of the size of the convolution kernels. So, if you see this network actually has a mix of 11 cross 11, 5 cross 5 and 3 cross 3 convolution kernels. So, let us just look at this convolution layer at the input. So, this one aspect of this network which is now highlighted in this figure is that the GPUs available at that time, the one this particular network was trained, had only 3 gigabytes of input of memory available. So, the computations for this network were split across 2 GPUs. So, if you look, we have split the network from the previous slide into 2 pathways. So, basically the top here, all the computation in the top of here would go to one GPU and all the computation at the bottom of here will go to another GPU. Okay. So, for the first layer we have 96 filter kernels as we saw. So, 48 of them in one and 48 of them in the other. Okay. So, if you look at the number of parameters here, it is very easy just to show an illustration of how to calculate the number of parameters. Let us say on just one pathway we have each filter has 11 cross 11 parameters. Okay. So, we have about 48 of them in one, okay. And there are 2 pathways, in this case GPU 1 again and GPU 2. So, it will about times 2 parameters per convolution layer in one convolution layer, okay. And it produces 96 of course feature maps. So, we have to that is why we have 48 times 2, 96 feature maps, okay. So, the size of the feature maps is 55 by 55. So, these are number of parameters. So, if you want to calculate the number of computations that you have to do per GPU for let us say number of computations per GPU. So, you have the output size is 55 cross 55 times 48. So, those are the total number of activations in the on one GPU in this particular computation layer, convolutional layer, and for each of these we have to calculate the this is the number of for each one to produce each output we have to do 11 cross 3 computations. Right. So, this is the number of outputs activations. So, basically 55 cross 48, and for each output we need to perform 11 cross 3 multiplications. I have ignored the additions that we have to do because it is the sum of products. You can also put in a factor there for it if you want to, but this is the typical way to calculate the number of computations. Of course, the network is spread across 2 GPUs. So, this is for one half of the feature maps. So, you have twice as many, okay. So, this is the typical computation number of computations that it is how you would calculate in a network, and the number of parameters. You see the number of parameters is quite less actually in the initial layers, right. And if you go to the final layer, again as I showed before in the earlier slides, you can at least for in between the 2 fully connected layers you can calculate. So, it is 4096 times 4096, this is the number of parameters. So, that is your weight matrix for a fully connected layer, which is that is how you would calculate for a regular artificial neural network. Of course, the number of parameters coming from the pooling layer to this layer is again much higher, because after the pooling you would have to unroll it and then to make it into a fully connected layer, okay. So, this is the typical computations required. So, a lot of the number of parameters here are huge. This is the number of parameters that I calculated, okay, but a lot of the computations happen in the earlier stage also. Okay, so, there is another innovation here. As I referred, I said that as 2 pathways. That is because if you look at how the training was spread across 2 GPUs, you will see that except for the layers where I have the cross arrows, these are the layers where I have cross arrows. In all the other layers, the ones here and here, the computations are restricted to the feature maps in that GPU. So, this has, so let us say if you look at this particular layer, this has 48 feature maps and we do a 3 by 3 pooling, but the pooling operation only draws from these feature maps. And when you do the subsequent convolution with the 5 by 5 kernel, then the 5 by 5 kernel actually acts across only these feature maps. That is why we call it the multiple pathways or 2 pathways, because and if you come here in this layer, then the output activation here also has feature maps, includes feature maps from both the GPUs. Okay. So, this one layer we have computations are involve both the or from feature maps in both the GPUs, while in the other layers they are done independently. So, this is like having a separate pathway, 2 different pathways in the network. Okay. And this is one of the networks, the first time use of ReLU. We saw that in the earlier slide, ReLU, non-linearity. It also used dropout regularization, we saw that earlier, dropout regularization. It also had dead augmentation. So, the data was, the images were augmented by, because you see the number of parameters is huge. There were a few million training images, but we have 60 million parameters, we do need more data if we have so many weights. It also used L2 regularization, okay, so that it does not overfit, to prevent overfitting to some extent. So, dropout and L2 as regularizers. See, the dead augmentation was done by flipping shifts, translations, as well as jittering the RGB values. So, they are done dynamically on the fly as the network was training. Okay. So, the network was placed first in the ImageNet recognition challenge, especially in the top 5 and the top 1 category. It had an error of about 15%, which was much higher than the second place finisher, again one of the earliest and the first CNN to win the ImageNet competition. So, this network sparked a huge interest in deep learning, because it had lots of parameters, it was quite deep, 7 layers, and if you include the max pooling also 7 weight layers, if you can call it that, because it had 1, 2, 3, 4, 5, 6 and 7 weight layers speak of, and of course interspersed with 3 max pooling layers. Okay. And it had a mix of filter kernels, 11 cross 11, 5 cross 5, 3 cross 3 kind of systematic. And if you also look at how the number of features increased as we go deeper into the network. So, in the initial layers we had, first layer we had 96 and then 256 here, because I am adding from both of the GPUs, 384 was preserved. Okay. So, as you go deeper into the network, the number of feature maps increased, the size of feature maps shrank, but the number of representations increased. Okay. So, this is a typical architectural design that most networks use even now. Okay. So, you would, as you go deeper in the network, there would definitely be decrease in the size unless you do zero padded convolutions, appropriate zero padded convolutions, but then you can always increase the number of feature maps to improve your representation. So, that is the general principle. It was also see that in LeNet 5, but it was much smaller in size because of the size of the input images as well as the the problem is concerned. So, it was just to recognize small images, okay, and they are also constrained by the computational resources available at that time. So, this was the AlexNet architecture. Okay. So, in summary, so AlexNet was the first network to be CNN to be used for the ImageNet classification challenge, produced state of the art results at that time. Okay, so it was about accuracy of 15%, had a huge number of parameters, about 60 million of them, most of the parameters towards the decision layer. So, basically the fully connected layers contributed to most of the parameters. It had the design principle was to use multiple size filters here, 11 cross 11, 5 cross 5, 3 cross 3, and the number of feature maps increased as you go deeper into the network. Okay. It had 2 pathways, the authors also report that having these multiple pathways actually improved their results. So, 2 pathways in the sense the computations were split across 2 GPUs, but if you see that, as we saw, the computations were not shared. Okay. So, except in one layer, 1 or 2 layers, especially here, not one layer, this layer here and towards the end the fully connected layers, that is where the computations were shared. Okay. Other than that, we can call this as 2 separate pathways. Okay. the results were reported based on an ensemble of about 7 networks, multiple networks, more than 5 networks. Okay. So, that lead to also an improvement about 2 or 3 percentage points. So, multiple and the layer normalization was also introduced here, but this particular layer normalization here is no longer used, but they do have a normalization layer in between the convolutional layers just before the input to the convolutional layer. Okay. So, now we will look at, in the next subsequent videos we will look at other architectures that performed that gave state of the art results on the ImageNet database.